Hello, hello, and we are ready to get into it. So the moment we've all been waiting for, we're going to start talking about the ellipsoid. There are a lot of similarities between working with ellipsoids and spheres, but those similarities will diminish very quickly as we get into it, as you'll see. So the ellipsoid is a more complex character than the sphere because the ellipsoid does not have a uniform radius between planes. So we're going to look at how we work with spheric or with ellipsoidal parameters. And just as a segue, we left off last time talking about convergence, and I hinted at where we were going by showing you the spherical convergence formula. And then I dropped this bomb, the ellipsoid convergence formula. And if you look at them, they're pretty similar with a little bit of a difference. So in the sphere, we use psi for a spherical latitude or a geodetic or geocentric latitude. And with the ellipsoid, we use phi, which is the ellipsoidal or geodetic latitude. If you look at these, for the most part, the formula are the same, especially if you relate this letter A, which we'll talk about what that is, with the radius of a sphere. And they have very similar and related definitions. This weird guy, this in brackets here, is really the main difference, and that is the defining feature or representative of the defining feature of ellipsoidal formulae versus spherical formulae. It's a way of accounting for the non-uniform radius that an ellipsoid experiences. So we're going to talk about what that is, what this guy is, sort of, and the role that this, it really comes down to this epsilon. Now, a lot of books, our book uses epsilon, that's eccentricity. A lot of other resources, such as the NGS, will use E, just little letter E for eccentricity. I'm going to try to use the epsilon since that's convenient, or since that's consistent with our text. But that will get us going on the ellipsoid. Now, the other thing I wanted to show you is, before we get too far, I made this blank diagram of an ellipsoid with some of the lines that we're interested in. And this is a PDF. The sole purpose of this is for you to print out 9 or 10 copies. You don't have to keep trying to draw ellipsoids. You can make nice big diagrams of the ellipsoid parameters. So if you print those out before we go forward with the video and have them ready, then you can just be labeling along. It'll be a real time saver and it'll help with clarity. Okay, that said, let's get into it. Let me scoot this aside and let's kind of develop the idea of the ellipsoid. A little dot there. So the Earth, whether you realize it or not, I'm going to exaggerate here, is not a sphere or an ellipse, and even taking the equipotential gravitational surface, which we'll talk about later in the term, into account, it's sort of this glob. It's very non-uniform. It's not a mathematical surface that renders itself readily easy to work with. So if this is the Earth, the actual Earth, our goal with an ellipsoid is to find a shape, a mathematically consistent shape that closely resembles the shape of the Earth. And in some places, the Earth's surface, the geoid, will be below the ellipsoid. In some places, it will be above the ellipsoid. So that that round shape, that blue shape, is supposed to be a perfect ellipse. But when we were talking about the sphere, we were talking about a shape that is uniform in radius. That is the z-axis, or the spin axis of the Earth, would be the same length as the equatorial axis. But in the ellipsoid, we find that, well, actually what we find, let me say it this way, what we find when we study the shape of the Earth is that it's slightly elongated along the equatorial plane. Elongated. And it's slightly shortened or compressed in the plane of the spin axis. Plane of spin axis. And it's compressed there. So that's where we get the ellipsoidal shape. Now, obviously, if we consider the, I don't want to say radius, but the length along the equatorial plane, it's going to be less, or I mean, it's going to be greater than the length along the plane of the spin axis, isn't it? So that uniform mathematical model that we use for our derivations and calculations. Need a color. That's what we call the ellipsoid. And you'll often hear it referred to as an oblate spheroid. Essentially the same thing, at least in terms of how we're going to use the ellipsoid. So ellipsoid or oblate spheroid. An ellipsoid is a, let's see, ellipsoid, I'll just define it really quick. Roughly, it's a surface called a surface of revolution, or revolve, or rotation, based on an ellipse rotated about the spin axis of the Earth. So we create this ellipse and we center the spin axis on the ellipse and then spin the ellipse around the axis, and that's a surface of revolution. So that is what we're going to use as an ellipsoid. Or that's what we're going to define as an ellipsoid. And for our purposes, it suffices. Now I'm going to bring in my diagram. Let me find it. There it is. And I'm just going to move it up to the corner here so I can make it nice and big. And this is identical to, in fact, this is what I made a PDF of for your blank diagram. And scoot it over so I have time, I have some room to write words. Okay. Okay, so the first question is why do we need to get so complex and use ellipsoids? Well, an ellipsoid model is necessary for precise engineering and or large area projects. The spherical model is great for resource grade mapping, for navigation, but if we're actually going to engineer a project such as an airstrip or a long bridge, then we need to use an ellipsoidal model to avoid systematic errors involved with design. And I posted a little article. It's very little. It's like a couple paragraphs, but it has a really neat picture. Let's see. I have it posted. There we go. So life without geodesy, sheer chaos. And it talks about, in a nutshell, the kinds of things, the kinds of problems that could happen if we don't consider the ellipsoid in engineering projects. And this is kind of a neat photograph. It's actually not a photograph. It's a dramatized picture of, what could happen if, a bridge is being built from each end, and we're not taking convergence on the ellipsoid into account when we're designing. The bridge ends don't meet in the middle, right? And we learned that even in a spherical sense, the forward and back azimuths are not equal. So in actuality, but if you start from either end using the same bearing, you're going to end up being off, right? Anyway, kind of a cool picture. It kind of drives a few things home. So ellipsoids are not new. Ellipsoids have been being used for quite a long time. And some of the early ellipsoids that we may have heard of, obviously, we have the Clark ellipsoid of 1866. That's the one that's based at Meade's Ranch, and that was used in the United States. So this was United States first, so the U.S. first ellipsoid. And that's the ellipsoid that was used for all of the early GLO projects. When they were figuring convergence, they were figuring it based on the Clark 1866 ellipsoid. Now, I say the ellipsoid a lot when I'm talking about ellipsoids, but there are literally hundreds and hundreds of ellipsoids that have already been developed, and in fact, there's an infinite number of possible ellipsoids we could develop. So Clark 1866 was the first in the U.S. Some other ones, there's a Russian ellipsoid called the, I have to be careful how I spell this, Krasovsky. And that's a Russian ellipsoid. And that was in 1940 that was developed, or somewhere thereabouts. What else do we have? We have the Helmert, which is European and is still used pretty extensively. And that's European, and that was about 1906 that was developed. And we'll get into how the ellipses are defined. Move this up just a little bit. And what the differences are between these. So anyway, there's many others. Many, hundreds, thousands. And the one that we use most commonly is the GRS 80. And then there's also the WGS 84, which is very similar to GRS 80. But for this course, we're going to be using GRS 80 ellipsoid as our foundation or our basis ellipsoid. Okay, so let's get into the anatomy of the ellipsoid. Let me drag my diagram down just so I don't have to, there we go. And I'm going to bigify a little bit. So what are the defining parameters of an ellipsoid? So just ignore the colored lines, the yellow, green, and red lines for now. But on an ellipsoid, the only parameters we need in order to define the ellipsoid in its entirety are this distance here, which we call A. I'll define these in a second, and this distance here, which we call B, where A is the length of the semi-major axis, semi meaning half, major meaning biggest, semi, I'll learn how to write here again. I always have to learn how to write. Semi-major axis. And B, as you might guess, is the length of the semi-minor axis. If we have those two if we have those two parameters of the ellipsoid, we can do all the mathematics we need. Those are the only parameters necessary. And you might think of it like on a sphere we use the radius for so much. Well, we have non-uniform radius on an ellipsoid, so we have to consider the difference between the semi-major and semi-minor axes, and then how those change along the surface of the ellipsoid. So throughout history, how have people approached, coming up with these semi-major and semi-minor axes to define an ellipsoid to meet their needs? So early ellipsoids, I'm just going to say EL ellipsoids, were either regional, or given a small enough country, they were or national, which means that in considering the definition of the ellipsoid, an agency or an individual or a creating body might try to fit the ellipsoid to a specific region, say a 1,000-mile by 1,000-mile region that's local to them. However, contemporary or modern ellipsoids are adapted globally, which makes sense with all of the satellite constellations and the interplay between the different nations' constellations, right? So modern ellipsoids are adapted globally. They try to take the shape of the Earth and find the best ellipsoid to fit it. Okay, so move my diagram down again. Actually, I'll just erase this. Just a little background and definition. So we have these lengths of the semi-major, semi-minor axes. Early ellipsoids, that actual A and B number is what would be reported. So we used to report A and B to define an ellipsoid. Now, what we use is something called flattening. Or we still use A. So we use A and flattening, or F. And then we also use eccentricity, which is really just, it's the same, it's really just a rearrangement of the terms involved in flattening. And we'll see that in just a second. And eccentricity, I'm going to try to use epsilon because our book uses epsilon. However, many resources use little e for eccentricity. I may screw up and interchange those, so I'll try to be consistent using epsilon, and then if I use e, just it'll be obvious within the context of what I'm doing. Okay, so those are the ellipsoid parameters. So what are those? What are those e and f numbers? So we know what a is. So we've gone over a. F is flattening. Which is given by a minus b over a. Put F equals a minus b over a. So in using this flattening parameter rather than b, you can see that the b is built into it. So as long as we know a, then we can, and we know a flattening number, we can pull b out if we want to. We can pull out the length of the semi-minor axis. Let's see. So if we just perform a little bit of algebra on that a minus b over a, we see that that's the same thing as 1 minus b over a. And that's a representation you'll probably always see at some point. You'll also see at some point is that 1 minus b over a, but you can see they're exactly the same thing, right? Okay. So why do we use, well, let me back up a second. This is how the flattening is defined. Now, what is really reported? Most often what is most reported is the inverse of the flattening. So why is that? If we already have this definition of flattening, which incorporates the lengths of our semi-major and semi-minor axes, why is 1 over f used instead of just f itself? If we look at, let me pull this up. I'll come back to the diagram here. Let's see, for example, GRS 80. The parameters are a equals 6, 3, 7, 8, 137.000 meters. B equals 6356 752 point, and this is a lot of point, so 0.314140 347 meters. The problem with using just A and B is there's often, as you can see, there are these big numbers, so they're awkward to work with. If we perform that, so F equals A minus B over A, which for GRS 80 equals, let's see, let me get back to that. If we just consider how similar A and B are in scope of their magnitude, if we divide A by B, we get 0.996, 647, 189, and it goes on and on and on and on. We find that they're magnitudes are so similar that the ratio is almost 1, right? So it's not very communicative to report A and B because we can see they're different, but by how much? So some problems. The difference between A and B, or A minus B, is so small that it's difficult, or I'll say ineffective, to communicate with. If we consider the flattening, for GRS 80, that if we do the math on that, we find the flattening, turn my page, F equals, okay, and I've got to copy this. This is a big number, so, or it's a tiny number, but it's a lot of digits. It's equal to 0.0033528 1068 118475. So not a really convenient number to try to communicate somebody as a defining parameter of an ellipsoid. So we use instead the reciprocal of that. So we can say 1 over f equals, and we'll look at it in a second. Let's see, for GRS 80, it's 298 point, a whole bunch of numbers. I'm going to give it in just a second, but let's compare it to the Clark ellipsoid. So GRS 80 has a 1 over f of, let's see, 298 and, yeah, 298, 257, 222, 100, 882. It's going to just keep going and going. 711, 243. Again, a lot of decimal places, but if we consider Clark ellipsoid, the 1 over f equals 294.9786 9821 3898. And no, I do not have these memorized, so that's why I keep looking down. But we can see just here, we can see the difference between the GRS 80 and Clark ellipsoid in terms of flattening. So it's much more readily apparent to work with the inverse of the flattening. There we go. So we're going to use 1 over f, a, b. There's one more defining factor, let's see, that we use called the eccentricity. And I'm just going to keep moving this up. So eccentricity. This is just another way of representing the flattening, or using it to define, using it as a parameter of the ellipsoid to make certain mathematics more convenient. I'll just say that. So epsilon is equal to 2 times the flattening minus f squared. The flattening squared raised to the 1/2. Okay, what does that mean? Well, not a lot, but keep in mind that all of these formulae are really just different manipulations of the A and the B, the lengths of the semi-minor and semi-major axes. That's the only parameters in these, because that's what F is based on, so therefore that's what epsilon's based on, or the eccentricity. And since this is a big ugly creature, usually what you'll see is epsilon squared equals 2f minus f squared. So if we take this eccentricity squared and plug in our definition of f, let's see, that would be 2 times, using that second definition of f, 1 minus b over a minus, all I'm doing is plugging in the definition of f, minus 1 minus b over a squared. And if I carry that down, if I do that math, then we find that the first eccentricity squared is equal to a squared minus b squared over a squared. So the a's and b's are still in there. And so I should say also this epsilon is often referred to as the first eccentricity. 2 C's. Which implies that there must be a second eccentricity, and in fact there is. So that second eccentricity is defined in terms of the first eccentricity. So the second eccentricity is E prime, or epsilon prime, and we represent it as a square, and it equals the first eccentricity squared over 1 minus the first eccentricity squared. Just a definition, no derivations there. So in summary, let me just sum this up so we have everything in one place. Ellipsoid parameters. Oop, I don't want that color. So ellipsoid EL parameters. Defining parameters. We have A, which is the semi-major axis, semi-major. B, which is the semi-minor axis. And then we have different comparisons of those. We have our flattening, which is A minus B over A, which is the same as 1 minus B over A. We have the inverse, which is just the inverse of that. Let's see, we have the first eccentricity, which is defined in terms of the flattening, it's 2f minus f squared, and the square root of that. And then I'll just say we often use the square of the eccentricity, of the first eccentricity, which is just 2f minus f squared. And then we have the second eccentricity, which we always talk about in terms of the square of the second eccentricity. And that is defined in terms of the first eccentricity, which is e squared, or epsilon squared over, I told you I would keep trying to use e, over 1 minus epsilon squared. So, and those are the parameters we're going to work with in computing all of the elements of the ellipsoid. And I should probably put in here the square of the first eccentricity. We saw we just reduced down. It's also equal to a squared minus b squared over a squared, which we'll use for some of our derivations, right? So if you copy down in your notes this page here, or this display, we'll be referring back to this over and over. So copy it down, highlight it, put a big box around it, put it in your summary of formulae, and we'll be referring back to that. So let me go back to my blank diagram, my blank ellipsoid diagram. I'll just pull it down here. There we go. What does all this mean? So we have our A and our B, our semi-major, semi-minor axes. On the ellipsoid, we can talk about 3 types of latitude. And we're going to just take these one at a time and talk about what they are. So I'm just going to erase the A and the B for now. We know what those are. If I were to consider, now just ignore all the lines that are on there, and if I were to consider a radial from the center of the Earth out to some point Q, we'll call it Q, and this is, I'll call C, the center of the Earth. The radial that extends from the center of the Earth to Q oh, come on. Those lines keep lightening up. Then this is exactly what we were talking about on the sphere. That is called still psi, like we've been using. That's the geocentric or Earth center latitude. And I'm not going to get too into that right now because we explored that in the spherical case, and nothing much changes with geocentric latitude in the ellipsoidal case, except that instead of using R, we're using some different, even the radii, we're going to use different representations of this type of radius, because if you'll note, remember, on an ellipsoid, that radius is not uniform like it was on the sphere. So that is geocentric latitude. The other type of latitude is, again, consider this point Q. This is the tangent to the ellipsoid, EL, at point Q. So that tangent is obviously perpendicular to the ellipsoid. And if we were to draw a line, a vector from Q that's perpendicular to that tangent, and extend it all the way to the spin axis of the Earth. That's that green line. In that case, we use a different symbol. We say phi. So that angle, which, by the way, is the same as this angle, there's all kinds of similar triangles here we're going to work with. So phi is geodetic latitude. And that's the one we're going to be most interested in here for a bit. Geodetic latitude is the angle formed between the ellipsoidal plane, or the equatorial plane. So I'll put EQ here. This is the equatorial plane. So phi is the geodetic latitude, which is defined as the angle between the equatorial plane and the normal vector to a point on the ellipsoid surface. Remember, we called that a normal vector. Normal oftentimes means perpendicular. So it's perpendicular to the tangent at the ellipsoid. And that's where we're going to stay for a bit. The third type of latitude I'll talk about later. But this phi, the geodetic latitude, can get pretty complex, and that's what we usually refer to when we talk about latitude on the ellipsoid. So let me just erase everything that's here, and I'm going to go over the anatomy of the ellipsoid. So to do that, I'm going to bigify my image because it's really hard to draw little things on this digital dry erase board. So we talked about, I'm going to use, let's see, what color should I use? I'll just use yellow again. Now we said this is our phi, or our geodetic latitude. Here's our normal vector. So this distance is our B. This distance is our A. Semi-major and semi-minor axes. The green line, we usually use N, and let's see, I need to write this stuff down. So N is the radius of curvature. That's terrible. It's called the radius of curvature in the prime vertical. Which I think is a misleading term. I really think it should be something more like the prime vertical extended, or the extension of the radius of curvature, and you'll see why pretty soon. But N is the radius of curvature in the prime vertical, long term for that normal vector. Let's see, P, if we look at this line here, well, we're going to call that P. And P, what do you think that is? It looks similar to what we've done before. That's the radius of the parallel of latitude. Radius of the parallel of latitude on the ellipsoid. Let's see, phi is geodetic latitude. I'll put it down here in the bottom right. Phi is geodetic latitude. Let's see. We have one more distance here. This here is z, which is just like in our Earth-centered, Earth-fixed Cartesian coordinates. That's the z. That's the z Cartesian coordinate. So z is geocentric z coordinate, which is kind of redundant, I know. Of a point Q. We're just calling Q right here. So z is the geocentric coordinate, or the xyz. You know, remember we called xyz the geocentric Cartesian coordinates? That's just the z geocentric coordinate. Okay, that's the basic anatomy that we're going to play with. So a couple of numbers that are really helpful. First off, if we can find a way to compute the radius of a parallel of latitude and the z geocentric coordinate, then we're going to go a long way to being able to define things like arc lengths and areas, lengths along a parallel, or m lambda, that sort of thing. So finally, we need a way to formulaically define our ellipsoid, right? So we know that the basic formula for an ellipse itself is x squared over a squared. I think that's right. Yeah. Yep. Plus y squared over b squared equals 1. That's just the basic formula of any ellipse. However, from our diagram, we'll use our notation. So the ellipse in our notation is p squared over a squared. That p is the radius of the parallel of latitude. And instead of y, we have z squared over b squared equals 1. And that's going to be important because we're going to derive that, that radius of a parallel of latitude. And since we need to know that radius of the parallel of latitude p, we're going to use as our vehicle the slope of that tangent line. Slope of the tangent line. Let's see. I'm running out of room to write. I'm going to erase a few things here. So what is the slope of that tangent line? There's a couple different ways we can get to it, right? We could say that the slope of the tangent line is the derivative of the slope of the tangent line at any point on the ellipse is just the derivative of the ellipse itself, right? That's how we find slopes of tangent lines. So what we need is to get slope of the tangent, we need to find dp of our ellipse. P squared over a squared plus z squared over b squared equals 1. So we're going to find that derivative. And I wasn't going to actually do it, but I think I will. Let me move this stuff out of the way. We're going to use implicit differentiation. So if we start with p squared over a squared plus z squared over b squared equals 1. First, we note that this is not an easy derivative to take in terms of explicit differentiation. So what we need to do is use implicit differentiation. So if I say that that is, I'm going to call that what? Well, we'll just leave it as is. We need to use implicit differentiation to get dz dp, which is the slope of our tangent line. For any point on the ellipsoid. Okay, so how do we do that? Well, implicit differentiation is a little bit of a different animal, isn't it? So we need to take for p squared over a squared plus z squared over b squared equals 1. We need to take the derivative of both sides, right? So we take d dp of p squared over a squared plus z squared over b squared. And we have to do it to both sides, right? d dp of 1. So let's do it. We're going to solve for our derivative. So I can use I forget which rule it is, but this is the same as, so my little yields arrow, d dp of p squared over a squared plus d dp of z squared over b squared equals 0. The derivative of a constant is always 0. And we have to remember that z, and this is why we have to use implicit differentiation, z is a function of p, right? Z equals some function of p. So that implies we're going to have to use the chain rule here at some point on this term. Let's do the next step. So ddp is equal to, we just use the power rule, right? That would be 1 over a squared times d dp of p squared plus d dp of z squared. I'm not going to touch that one yet. Over b squared. Well, I will just a little bit. I'm going to make it, I'll do the same thing I did up there. 1 over b squared, remember that's just a number, times d dp of z squared equals 0. And then we just do this derivative, this first derivative, and we have 2p over a squared plus 1 over b squared. And this is where we have to be careful and use the chain rule, right? So the chain rule is the derivative of the outer times the derivative of the inner. So times the derivative of the outer, which is 2z, times the derivative of the inner, which is dz dp, equals 0, right? And so now we're ready to go the next step. This is just the chain rule. Nothing scary here. Now we can solve for dz dp, right? If we solve all of this, we get, change colors here. We can solve for dz dp, which is the implicit differentiation part, and we get dz dp equals minus p b squared over z a squared. And that is the slope of our tangent line at any point on the sphere. Remember, p is like our x coordinate, z is like our y coordinate. So, cool. That's the slope of tangent on an ellipsoid at any point. So there we go. That's sort of an introduction to the ellipsoid. You want to make sure that you have this clearly understood. Understand how it's derived, and then keep that in your notes. We're going to use that as we move forward into deriving one of the ellipsoid formula. And once we go through that, you'll see why I'm only going to derive one of them. The other formulae are similarly derived, but it's not a trivial derivation. In fact, the derivation itself will probably take an entire class or an entire lecture. So anyway, with that, we now have the definitions and the tools and the language to start talking about the ellipsoid. As usual, if you have any questions, reach out, send me emails. I've been getting questions quite a bit, which I like. And we can set up Zoom sessions. We have our regular Zoom sessions, and that's it. So until next time, have a great day.